Hi, welcome to our video on igneous rocks. If this is one of the first videos you're watching for environmental geology or another class, I really urge you to treat this video just like a classroom lecture. Take careful notes on the video that follow the stated organization, and that's going to help you manage all this information and turn it into a cohesive framework for yourself. So please take notes, listen carefully, because the reason you're watching this video is to try and learn this information as best you can. So this video is on igneous rocks, and I'm opening the video with this shot captured from the Mars Curiosity rover just after it had landed on Mars. What is it looking at? It's looking across this barren plain of the Mars surface. And these rocks here are all chunks of basalt. These are igneous rocks. And the reason that's important is right away, seeing these igneous rocks tells us something about the history of the Martian planet. It tells us that these igneous rocks must have been produced by melting of an original source rock, and that melt had to rise to the surface as part of some plate tectonic cycle. Once we analyze the chemistry of these rocks, we'll be able to learn even more about how quickly that tectonic cycle happened, what the raw ingredients were, and what the conditions were of Mars' early geologic history. So the point is this: igneous rocks, like these basalts on Mars, and like all rocks, hold a record of Earth history, and it's the geologist's job to learn how to interpret that record. So in this video, I want to teach you some basics about igneous rocks that would help you start to be able to make some of these interpretations. So the video will start out and we'll look at rocks versus minerals. Then we'll look at the characteristics of igneous rocks, both in terms of composition and in terms of grain size. Okay? Then we'll finish with a quick bit on how igneous rocks tend to occur in nature, with examples of both plutons and dikes. So first, what are minerals? People always confuse minerals and rocks, so it's really important to get these straight. Minerals are the building blocks of rocks. They are crystalline solids that form in a natural environment, okay? So they have a kind of molecular crystal structure. That crystal structure repeats itself in an organized way, and they have a constant composition throughout. That's really key. Rocks may be made of a hodgepodge of minerals, but minerals in turn have a constant composition throughout them. Now rocks, in contrast, are composed of different minerals. Okay? So for example, this was the mineral olivine that we just looked at, and here's the rock basalt. Basalt is made of a bunch of fine-grained minerals that you can't really tell what they are. That's what the black is. But then also these larger olivine crystals embedded in the matrix. So the rock does not have a constant composition throughout. It changes. But it is made up entirely of different minerals, including olivine. It's also important to note that rocks can be composed of fragments of other rocks. For example, most sedimentary rocks are composed of recycled rock fragments. Okay, so now that you've got that straight, let's look at the characteristics of igneous rocks. How do we classify them and identify them? Well, first we need to understand where they form. What defines an igneous rock is that it is a rock formed when minerals grow in a liquid magma as the magma cools. All right? So imagine you're sitting above a subduction zone, for example. You've had some melting in the crust, and it's created a big chamber of hot molten magma that's a liquid, right? As that magma starts to cool, minerals start to crystallize. And eventually, once this is entirely cooled, it has entirely crystallized into minerals, and it is now a new type of rock. Specifically, it's an igneous rock. And we can identify igneous rocks because they have a very characteristic relationship between the minerals within them. Specifically, They have intergrown, angular, and randomly oriented minerals. Okay, there's no layering. The minerals seem to interlock like a jigsaw puzzle. The minerals tend to be angular and kind of random in size, showing that they grew in essentially an unconstricted environment. As these minerals each grew larger, they kind of bumped up against each other and they were each able to take on a shape. They don't have fabrics or layers. So now you have a sense of where they form and kind of what they look like in terms of their texture. Let's talk a little bit about their composition. So we can divide up igneous rocks, and all rocks really, in terms of their composition. And we broadly can talk about the rocks being felsic or mafic. Okay? Felsic rocks are those that are rich in silica, sodium, potassium. Mafic rocks are rich in iron, magnesium, calcium. Okay? And so this diagram is a bit of a Rosetta Stone that helps us categorize and think about igneous rocks. It's a little bit complicated, so I'll walk you through it quickly. Up here, we've got essentially the composition of the different rock types, from felsic on the left over to mafic and ultramafic on the right. Okay? Down here on the bottom, there's just arrows showing that if you're a mafic rock, you have increasing iron, magnesium, calcium to the right. And if you're a felsic rock, you have increasing potassium and sodium and silica off to the left. Okay? So felsic's over here, mafic's over here. This main panel shows the mineralogy of these different igneous rock types as terms of percent of the rock by volume. Okay? So imagine a felsic rock, which might be called a granite, for example. That's going to have roughly 5% muscovite, roughly 20% quartz, roughly 50% potassium feldspar, and so on. And so the key idea here is that these different minerals have different compositions. So if you're made up of these specific minerals, in general, that's going to leave you rich in silica, potassium, and sodium because these minerals themselves are rich in silica, potassium, and sodium. So we can kind of think of this in terms of the minerals have a chemical composition, which then ultimately defines the chemical composition of the rock that those minerals will make up. So you don't need to memorize this, but we'll be using it in class and lab as a handy reference. So let's look at a few examples, and I know you've seen these in your own life. Here's a felsic rock, a granite, and here's a mafic rock, a gabbro, okay? And in general, you'll note that the mafic rocks tend to be darker. Those minerals that are rich in iron, magnesium, calcium, they tend to be dark, whereas minerals that are rich in sodium, potassium, silica tend to be light. So it's fairly common that most felsic rocks are lighter in color, most mafic rocks are darker in color. Now, but that's the other characteristic that you can use to classify rocks is texture or grain size, okay? And so here's the same slide I just showed you with the granite and the gabbro. But now take a look. Here is the fine-grained equivalent of a granite. It's called a rhyolite. And here's the fine-grained equivalent of a gabbro, which is called a basalt. So these have the exact same composition. It's just that this basalt cooled quickly, and so the minerals weren't able to grow to a large size, whereas the gabbro cooled slowly, giving time for those mineral crystal structures to assemble themselves. And the result is a coarse-grained gabbro versus a fine-grained basalt. And it's the exact same here with the granite and rhyolite. They have the same composition. Granite just cooled slowly with big minerals. Rhyolite cooled quickly with small minerals. Okay? And typically, one way to cool quickly is to essentially be erupted at the surface. So it's quite common that rhyolites and basalts are what we find in lava flows. where a magma chamber has essentially erupted to the surface, created a lava flow that then cooled almost immediately. There was no time for the crystals to grow large, so the rock just quenches and we get a fine-grained rhyolite or a basalt, usually associated with that volcanic eruption. So let's finish the video by looking at a couple other examples of how igneous rocks occur in nature. And here's a little diagram that shows kind of an idealized igneous system, again, perhaps sitting above a subduction zone. We tend to have magma coalescing into these big magma chambers, which cool over time. So these red ones are active. These ones here show older magma chambers that may have already cooled in a previous generation. And these magma chambers tend to feed plumbing above them. For example, a volcanic pipe leading to a volcanic eruption, or dikes, which we'll look at in a second. And of course, here's the lava flow that we just talked about in the previous slide. So right now we're going to talk about slow cooling within these magma chambers. Once these have cooled, they form a body of rock called a batholith, or a pluton. That's a slow-cooled magma chamber. A great example of this is the Sierra Nevada mountains in California. Huge, thousands of miles long, hundreds of miles wide, massive mountain range, which is made mostly of cooled batholiths and plutons, which were emplaced above an ancient subduction zone. And that slow cooling led to coarse-grained, very homogeneous granites, such as this example from Half Dome in Yosemite National Park. Another example, if you ever get the chance to visit Patagonia in southern Chile, you'll find a lot of large batholiths in that area too. For example, the famous Torres del Paine National Park in Chile. Here we have a beautiful granite batholith, and actually perched on top is the overlying country rock that actually was the roof of that magma chamber. This is the rock that was there before the magma chamber was intruded. Beautiful relationship. And the final example of an igneous feature I want to talk to you about is a dike. A dike is a sheet of magma that is injected upward from a magma chamber, okay, in a thin sheet, typically 1 to 3 meters wide. Now, because that's so thin and it's being injected up into cold host rock, these dikes cool slowly and acquire a very fine-grained texture, okay? Here's an example of a dike in the western U.S. You can see this planar sheet, literally, that's been weathered out of the surrounding rock. So you can see that this dike was intruded upwards into the surrounding rock, and it's clear to see that the dike cross-cuts that surrounding rock, demonstrating that the dike is actually younger and was intruded into that surrounding rock. Now in this case, we get this neat kind of protruding geometry here because the dike has that fine-grained igneous texture, which has made it much slower to erode than the surrounding country rock. So in this case, the kind of surface geometry we're left with that highlights the shape of the dike is really the result of differential weathering, where the dike was resistant and the surrounding rock just weathered away over time. So in summary, in this video you learned that minerals have a constant composition and a repeating crystal structure. Rocks are made up of minerals or sometimes of recycled rock chunks. We then learned that mafic igneous rocks tend to be rich in iron, magnesium, and calcium, and felsic rocks tend to be rich in silica, sodium, and potassium. We can name igneous rocks based on either their composition or their texture, i.e. their grain size. If a rock is coarse-grained, it means it cooled slowly. If it's fine-grained, it means it cooled quickly, for example, in a lava flow. And then other common types of igneous rocks that we see are batholiths, which are cooled magma chambers, and dikes, which are sheets of magma intruded upwards from a magma chamber. Here's a couple of concept questions which you should be able to answer. And I'll just remind you that these concept questions will ultimately be used as exam questions in this class and also as quiz questions. Thanks a lot. Bye.